This is mathheals.com, where you can find more links to math and computer science YouTube videos. Let's take a look at related rates. And to understand more about this, let's say we take a sphere, ball-shaped object. Now, going out from the center out to the surface in any direction, that'll be our R. And as we increase R, as the rate of R changes, then the volume will change also. Also, the surface area will. While the R may grow linear, like if you start out with 4 and then you take it to 8 doubles, you'll find that the volume will not have the same rate of growth. So that's what this section is referring to, is related rates. Whereas you change one, another one changes. Let's look at our first problem here. We got x squared plus y squared is equal to 5. And we're going to put, in terms of this section, this lesson, we're going to take derivative with everything with respect to t, like time. It says assume that x and y are both differentiable functions of t and find the required values of dy dt and dx dt. Well, we're going to take derivative of everything where it's sitting with respect to t. This is implicit differentiation. Now, here we have to x squared. We take derivative just like normal. This is 2x. But we're taking the derivative with respect to t, and this is really an x. So whenever you have a different variable, you take the derivative just like normal, but then you have to add on your dx dt, or whatever variable you're working with. Now, y squared becomes 2y, but again, it's not y, is it? So we have to add on our dy dt. And 5 is just a constant, so that just goes to 0. Okay, so now we'll do parts A and parts B. Part A says find dy dt when x is equal to 2, y is equal to 1. So x is equal to 2, y is equal to 1, and dx dt is equal to 5. So we'll go up to our equation up here. We got 2x dx dt plus 2y dy dt equals 0. And actually, they're all divisible by 2, aren't they? So I'll go ahead and drop the 2's. So then I'll plug 2 in for the x. dx dt we said was 5. And again, that 2's gone. We said y is 1. And we're trying to find dy dt on part A. It says find dy dt. Well, 2 times 5 is 10. Plus dy dt. Now I'm going to take that 10 to the right side, and we got dy dt is equal to negative 10. And that's our answer. Now for B, they say x is equal to 1, y is equal to 2, and dy dt is equal to negative 3. And they want us to find dx dt on this one. I'm going to go back up to my equation up here. I'll drop the 2's though. So plug 1 in for x. We're trying to find dx dt, so I'll leave it alone. Plus y, which is 2, times dy dt, which is negative 3, equals 0. So that gives us dx dt minus 6 equal to 0, or dx dt is equal to a positive 6. And that's the last thing they're asking for. So those are our answers. Let's take a look at this one. I think I have room, hopefully. Okay, find the rate of change of the distance between the origin and a moving point on the graph of y is equal to cosine x if dx dt is equal to 5 centimeters per second. Rate of change of the distance between the origin and a moving point. Between the origin and a point. Origin's a point, so a point and a point. Well, this is a distance formula. So we're going to have 2 points. Now our first point, between the origin, well, that's 0, 0. That's the origin. And then our second point. It says a moving point on the graph of y is equal to cosine x. Well, this first part is our x, and the second part is our y. Well, they tell us what y is. They say y is equal to cosine x. So we're going to have x cosine x. And this is our moving point. Now our distance is going to equal to the square root of y2 minus y1 squared plus x2 minus x1 squared. And this is our first point, so this is x1, this is y1. This is our second point, so this will be x2, this will be y2. So we'll have cosine x minus 0 squared plus x minus 0 squared, which gives us cosine x squared plus x squared, which is the cosine x squared plus x squared, all of it to the 1/2 power. Well, they also tell us dx dt is equal to 5. So dx dt is equal to 5. Now we're going to take the derivative of everything where it's sitting with respect to t. So we'll take the derivative of capital D with respect to t. And I should have wrote that a little bit differently. There we go. There we go. And we'll take the derivative of this side with respect to t. There we go. Well, whenever you have a single variable like you do on the left side here, it just goes up on top like that. Always. Over on the right side, we got brackets to the 1/2 power. This is the chain rule, specifically the general power rule. If you got something inside of brackets to a power, you take your power, put it out in front. What's inside your bracket remains as is. Lower your power by 1, and then you multiply it times the derivative of what's inside the brackets. So multiply it times the derivative of cosine x to the second power plus x squared. Well, the got 1/2 here, and then this is cosine x squared plus x squared. 1/2 minus 1 is negative 1/2 times the derivative of this. Well, this is cosine to the second power. Well, this is the chain rule again, general power rule. You got parentheses to a power. So we're going to take our power, put it out in front. What's inside the parentheses remains as is. Lower our power by 1. And then we're going to multiply times the derivative of what's inside the parentheses. Well, derivative of cosine is negative sine. Plus, and x squared becomes 2x. Now we have to add on our dx dt here. Some books you'll see will put it on both pieces here, since you got a plus between them. But you could equally just put it to the side like this. Okay, so that gives us, guess I'll merge these into one fraction. Got a 2 downstairs. This negative power goes down below. So we got cosine x squared plus x squared, all of it to the positive 1/2. This is going to go up on top, so we got a negative 2 cosine x sine x plus 2x, and then dx dt. Now, the information they're giving us is dx dt, so we can plug that in. They tell us that's equal to 5. And notice how the top part here, they both have 2's, so I can factor that out. And that gives us negative cosine x sine x plus x over 2, and then cosine x squared plus x squared to the 1/2. And we said dx dt, what did we say that was? 5. Well, those 2's going to cancel, and we'll have a 5 up on top. So we'll have 5 times negative cosine x sine x plus x over, actually I put that back in square root form now, because the 1/2 power is the square root of cosine squared plus x squared. And that's our change of the distance with respect to time. Now this would tell us, if we put in our different x values, whatever we're studying, this would tell us what how the distance is changing, the rate of change of it. It wouldn't tell us the distance. It would tell us how much is changing, the rate. So keep in mind what you're finding on that. Well, I guess what is this called? Related rates. Calc 1, related rates, page 01.pdf. There we go. That's a bizarre message. Let me save it again. I don't think it has anything to do with the error message that popped up. Yeah, it looks like I got that there. Okay. I was having a little bit of trouble earlier with the equation editor, and it was probably still running, and finally gave up the ghost and died off. Okay, let's look at a third example. The radius r of a sphere is increasing at a rate of 5 inches per minute. R is increasing. That's a dr over dt. This is increasing at a rate of 5. Now, if we were in physics class, you'd want to keep these units of measure in here, but we're not in physics. We're in calculus, so I'm not that worried about them. They give us the formula. V is equal to 4/3 pi r to the third. It says find the rates of change of the volume. So they're wondering the rate of change of the volume. dV over dt is equal to something. When r is equal to 10 and r is equal to 20. We'll come back to that. Well, we're going to take derivative of everything with respect to t. So we'll take the derivative of v with respect to t. And we'll take the derivative of 4/3 pi r to the third. Now, remember, when you have a single variable like this v, this just becomes dv dt. Over on this side, the 4/3 pi, that's just a constant. Both those are just numbers, so you just put those out in front. We don't worry about those. Now, the derivative of r to the third would give us 3r squared, but then we have to add on dr dt, because we're taking the derivative with respect to t, and these are r's. So whenever you have different variables like that, you always have to put this on. Well, the 3 is going to cancel, and we got 4 pi r squared. dr dt we was told was 5, so I'm going to plug that in. So then dv dt is going to equal to 20 pi r squared. Now they want us to plug in r is equal to 10, and they also want us to plug in r is equal to 20. So let's put 10 in for r. So we've got dv dt is equal to 20 pi times r squared, so times 10 squared. That gives us 100. 100 times 20 gives us 2,000, I believe, pi. Now in this one, we'll go back to our equation down here, our formula, and we'll plug in 20 for r. So I've got 20 pi and then r squared, so 20 squared. And let's see, 20 squared is 400. So that gives us 8,000 pi. And those would be our rates of change of the volume with respect to t. Let's take a look at this one. It says all edges of a cube are expanding at a rate of 4 centimeters per second. How fast is the volume changing when each edge is... So we've got a cube, and each of these sides will be S. I think that's normally what to use. And the way the cube works, so I can't draw it, is going back here, the depth will also be S. So our volume is equal to S times S times S. So S to the third. That's not a 5, that's an S. Let's see what they're giving us. All edges of the cube are expanding at a rate of 4 centimeters per second. They're telling us that ds over dt is going to equal to 4. How fast is the volume changing? So they want to know what dv dt is. And specifically when each edge is 2 and 20 centimeters. Okay, well let's take the derivative of each side with respect to t. Take the derivative of v, and we'll take the derivative of s to the third. Now this just gives us dv dt. Now the derivative of s to the third is 3s squared, but since we're taking the derivative with respect to t, and this is really an s, we have to add on our ds dt. Well, up above here they tell us ds dt is 4, so we'll put 4 in. So we've got 3s squared times 4, or 12s squared. And that's our dv dt. Well, A says when s is 2. And the other one is when s is 20. So we'll now take what we have right here, and we'll plug in these values. So we're going to plug 2 in for the s. So we've got 2 squared, which gives us 48. And over here, if I put 20 in, so I've got 20 squared, 12 times 400 equals 4,800. Now the S is in centimeters, and of course volume is always cubic centimeters, so I know what this change is just right here. You can see going from 2 to 20, it changes dramatically in terms of the volume. And let's save that. And time for a little tablet to blow up, so let me bring up another copy. There we go. And let's look at our next problem. The formula for the volume of cone is V is equal to 1/3 pi r squared h. Find the rates of change of the volume, rates of the volume. So they want to know dV dt, is what that's equal to. If dr dt is equal to 4, and h is equal to 6r. Well, to begin with, the telling us this h is 6r, so I can go ahead and plug that in. If we plug that in to begin with, it makes it easier. There we go. Well, 1/3 times 6 gives us 2. Pi r squared times r is r to the third. Well, we want to take derivative of everything where it's sitting. So we'll take derivative with respect to t of v. We'll take the derivative with respect to t of 2 pi r to the third. Whenever you have a single variable, again, this just becomes dv dt. Over on this side, 2 and pi are both constants, so those just come out in front. The derivative of r to the third is 3r squared. Take derivative like normal, but since we're taking the derivative with respect to t and it's really an r, we have to put on dr dt. 2 times 3 is 6, so we got 6 pi r squared, and dr dt we were told was 4, which gives us 24 pi r squared. Okay, now they want to know it when r is equal to 3 and r is equal to 12. So this dv dt, change of volume with respect to time, is 24 pi times 3 squared. 3 squared is 9. Which would give us 216 pi, I think, barring any basic math error. Now the other one. We're going to find how much the volume is changing with respect to time once r is equal to 12. So we got 24 pi times 12 squared. And where's my calculator? I'm not going to do this one by hand. 12 squared is 144, but let's see, 144 times 24. 3456. So 3,456 pi. And those will be our answers. Let me get a drink here. Okay, number 6. It says a 10-meter plank that was originally lying flat on the ground is pulled up the side of a building. Here's my building, and here's my plank. Now the plank is 10 meters. It's pulled up the side of the building by means of a rope tied to the end closest to the building. So there's a rope tied to this end, and it's being pulled up. So as it's pulled up, it forms a triangle. Now this is always 10 meters. That doesn't change. So as you pull this side up, it drags this side closer. Okay. It is pulled up at the rate of 0.25 meters per second. Well, if we think of this as a triangle, here's what it looks like. This would always be our 10. This is our plank. And of course, this is our x and this is our y. So when they're telling us it's pulled up at the rate of 0.25 meters per second, then the change in y with respect to t is going to equal to 0.25. Now you have to decide whether it's positive or negative. Well, initially my plank is flat on the ground, which means y is equal to 0. As it's pulled up, then the y increases. So that's why I know it has to be positive. How fast is the end of the plank on the ground moving along the ground when it's 3 meters from the wall? So they're asking when this is 3. So again, it's x equals 3. Well, they want to know how fast it's moving, so they want to know what dx dt is doing. Well, I can find out the distance of this side here, because this is a right triangle. So this would be y. So we're going to have x squared plus y squared is equal to r squared. So we got 3 squared plus y squared is equal to 10 squared. So we got 9 plus y squared is equal to 100. Take the 9 over. We got y squared is equal to 100 minus 9, or y squared is equal to 91. So y is going to equal to the square root of 91. Now, we got a formula for this, which we can use over here. So, so what is it asking? How fast is the end of the moving? Okay. So we're going to have x squared plus y squared is equal to, and r is already set. It's no matter what, it's always 10. So I can just go ahead and put 10 in there. X and y are changing though. So we're going to take derivative of everything where it's sitting with respect to t. So take derivative of t, or derivative with respect to t of x squared. Derivative with respect to t of y squared. And then the derivative with respect to t, 10 squared is 100. Take derivative just like normal, so this becomes 2x, but then we have to add on our dx dt. Because again, we're taking derivative with respect to t, and it's really an x. Over here, this becomes 2y, but we have to add on our dy dt. And this is 0. Now I can divide everything by 2. We've got x dx dt plus y dy dt equals 0. Now they tell us dy dt is 0.25, so we can plug that in. They also tell us x is 3, because that's what we're wondering, what's the rate of change of x when x is 3. Y we found was square root of 91, and we already said dy dt is 0.25 equal to 0. Okay, well, I want to solve for dx dt, so I'm going to go ahead and take that square root of 91 times 0.25 to the right side, and we got negative square root of 91 times 0.25. Divide both sides by 3, and we got dx dt is equal to negative square root of 91, 0.25 over 3. Different ways you could solve this one. If you want to leave it in the exact form, then we could change the 0.25 to 25 over 100, or 1/4, and reduce it from there. If we did that, in case you're curious, this would become negative square root of 91 times 1/4 over 3. And you take that denominator, put it down with this one, and this gives us negative square root of 91 over 12. Or we could get a decimal approximation. Negative square root of 91 times 0.25 divided by 3. And that's approximately negative 0.79. meters per second. Looking at our unit of measure. Again, I'm not that concerned about units of measure because we're not in physics, but we'll go ahead and save that. And I believe that's the last slide. Yes, it is. So I'm going to stop the recorders.